Hello, everyone. Welcome to today's live broadcast, Samples and Data, the Two Layers of Integrations. I'm Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. Today's webcast is presented by LabRoots.com, the leading social media site for science professionals, and sponsored by Beckman Coulter Life Sciences. Beckman Coulter Life Sciences develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. More than 275,000 Beckman Coulter systems operate in both diagnostics and life sciences laboratories on 7 continents. For over 75 years, our products have been making a difference in people's lives by improving the productivity of medical professionals and scientists, supplying critical information for improving patient health, and delivering trusted solutions for research and discovery. To learn more about Beckman Coulter Life Sciences, please visit www.beckman.com. Before we start, there are a few instructions. We want to hear from you during this interactive broadcast, so please ask questions or leave us a comment. Answers are welcome too. You can do this by hitting the green Q&A button at the lower left of the presentation window and typing in your comments and questions. We'll try to get to as many as we can, and we'll follow up if we don't have time today. Want a better look? You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you can't hear or see this presentation properly, let us know by clicking on the support button at the top right or use the Q&A button. We'll make sure we try to resolve any issues. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Now let's get right to today's presenters. We are proud to welcome Dr. Russell Green, Project Manager, and Tim Sherrill, Staff Systems Engineer, both from Beckman Coulter Life Sciences. Russell Green has a degree in biochemistry and molecular biology and a PhD in crystallography from the University of Leeds in the UK. He worked in research for 2 years at the University of Leeds, then moved into a role as an automation specialist before taking on project management duties in the UK in 2010. Russell then moved into the EMEAI marketing team as a field marketing manager in 2012. He is a 10-year veteran of automation at Beckman Coulter. Most recently, Russell returned to project management by leading the developed markets team for automation. Tim Sherrill works in the Integrated Solutions Group. He received a degree in computer science from the Rose-Hulman Institute of Technology. Tim has spent his career with Beckman Coulter in the areas of software research and development, custom engineering services, field project management, and life science automation. His projects have focused in the areas of automated data processing and last year on a new version of Beckman Coulter's data management product, DART. I will now turn the presentation over to Dr. Russell Green and Tim Sherrill.
Thank you for the introduction, and thank you for joining today. So this is a 2-part presentation. I'm going to give the first part of this, and just to guide you through what we're going to be talking about today, I'm going to start off by a very brief run through our Biomek Continuum, so our collection of automation products, just to give you some context as to the breadth of solutions that we were trying to address with the kind of options we're talking about today. And then I want to go into some of the challenges that we face in cell culture automation in particular. We will later on be focusing on a cell line development workstation, but broadly speaking, the challenges that we see when working with cells and trying to culture them are fairly similar regardless of the scale of automation that we're talking about. I then want to speak to the software solutions that we have for controlling those workflows before going into that example cell line development system and some of the devices and challenges that presents to us as well. And then I'll hand over to Tim, who will talk through how we then would solve the data problems for cellular workflows. And hopefully you'll see as we go through this talk that many of the challenges we face are really software or data issues. And although once we have the hardware, we may have all the pieces on there, really how we control them and how we handle that data is really how we solve a lot of these particular problems specific to cell culture. So this slide represents our current portfolio of automation products, and I don't want to spend too much time just dwelling on these products, but suffice to say that moving from bottom left to top right, we have an increase in potential productivity and system capability. And you can see, starting at the bottom left, we have an entry-level liquid handler that we call the Biomek 4000, and we pass up through our various Biomek liquid handlers, including the new Biomek i5 and i7 platforms, up to integrated systems where we add on devices a little bit like building blocks to build out functionality for more complex workflows. Now this is worth showing because when we look at cell culture systems, we face similar challenges regardless of the spectrum, and we also have a broad portfolio of installed base of cellular systems. So again, I have a similar chart just showing increasing throughput capabilities on the vertical axis, and then the complexity of the system or the degree of automation or walk-away time on the other axis. And you'll see as I present some of these systems, and these are all live systems that are out with customers right now, you can see everything from that simple Biomek 4000 benchtop liquid handler up to the integrated systems. And just to highlight a couple of these in particular, that Biomek 4000, we place several of these that really just do simple media exchange for a small number of plates. On the top left, we have what is essentially a straightforward liquid handler attached to large capacity incubator in order to do a huge amount of media exchange, so for some cell line maintenance activities. On the bottom right, we have a more complex liquid handler, which you can't see on this image, but has some capabilities integrated on deck, attached to a relatively small incubator. Now what that system is doing in this particular example is 3D cell culture, which has a much more complex workflow, and we're only ever running a throughput of plates in the order of 10 to 20. And then finally, the other one I'd like to highlight is in the top right. At the high end of the spectrum, this is a large system with both high throughput and high complexity, which is designed to do cell line maintenance for some 40 cell lines simultaneously over the course of many months. So you can see that we have a spectrum of systems here that address a variety of different cell culture challenges. Now, what I wanted to go through on the next couple of slides is just some of the challenges in particular, I can't go through all of them, that cell culture presents to us, and how we solve a couple of them that are actually common throughout all of these systems. So what does cell culture present to us as an automation vendor? Well, the first challenge is that typically this is very long processes. They can be weeks or months. And one immediate challenge for us is that most software that liquid handling or automation vendors supply is really only designed to cover a run within a day. And so what I mean by that is, within a day I may want to do 40 plates worth of media exchange. That would be a day's worth of activity, and a lot of software is designed to cope with that. But the question is, how do we then link together those processes that make that into a full cell culture workflow, from cell seeding right through to some kind of harvesting? There's typically a large amount of labware in the system, obviously not at the very low end. This is specific to the medium or higher throughput systems, where it doesn't take a lot of rocket science to calculate that if you go from some cultures in a 96 well plate and you want to expand every well up through 24 and 6 well plates and finally into a 1 well plate or a flask, that you're having an ever-increasing amount of labware in the system over time. There's a lot of data, and this is one of the key things we want to talk about today, and that data could be sample identifiers, it could be volume information, it might be what type of media do I need to use, it could be data that we've gathered on the system, such as confluence, and we'll come back to this later on and how that might drive what is a hit for us to carry on through. That data, as I just alluded to, can drive decisions. I want to passage my cells at a certain confluence, and every well goes at a different rate, and so I need to make a decision about how I handle my labware at a well-based level, because biology doesn't work in a uniform way. Very often I have large volumes of media, so liquid handlers in the market that we're talking about here tend to operate in the microliter to milliliter range, whereas the amount of media that we might need for a process is typically in the hundreds of mils, if not liters. And so we need to have some solutions that deal with that, and of course we don't want to shock ourselves by pouring cold media on top of them, and so we need to have some way of delivering nice warm media onto the deck of the robot, into the cells. We also need to handle liquids in a very careful way, and this is one of the things I'll speak to in a bit more detail. Automation can't do everything a manual pipetter can do. We move in a specified set of axes that doesn't have the same twisting motions, for example, that a human hand might have. But we can do certain things to emulate that, and I'll come back to that in a moment. Of course, adherent and suspension cells require very different considerations. You may need to integrate a centrifuge for suspension cells in order to do a splitting or passaging exercise. And last but certainly not least, system sterility. There are a number of ways that we can approach that, and that's not something I'm going to speak about in much detail today. So how do we solve these problems that I've thrown out there as fairly consistent problems we face in cell culture? So the first one I want to talk about is handling delicate cells, and this is about pipetting control. And again, this is primarily a software issue. So when most liquid handlers out there, we all have the ability to move liquid up and down, but clearly if you want to be more careful with your pipetting, it's a software control issue. How do I control the speed of that? How do I move around whilst pipetting to create a particular motion? So the question is, can an automated liquid handler manipulate cells as well as a human? And the answer is actually yes. Often people think no, but the answer is yes, but with some particular considerations. And it's very common that when we automate a process, you do have to tweak some things. How do we pipette cells gently? Well, Biomek systems can control their speed at a very fine level and also move whilst pipetting. And this is really key. You can imagine if you just were to go to the center of a well and very rapidly dispense media into it, you're probably going to create some kind of dead patch of cells in the middle, or at least blast those to the edge of the wells. What we would tend to do is move the pipetter around whilst pipetting that media much more slowly so that we're not impacting on that adherent layer of cells on the base of the plate. Similarly, how do we remove media without disturbing cells? Well, if it's a small well plate, and what I mean by that is something like a 96 well plate, we can simply move our pipette tip to the side of the well and aspirate, and normally the surface tension is sufficient to aspirate the liquid. We could actually potentially move our pipette tip around the edge of the well to drag up those last few droplets if required. If we move on to larger well plates, so something like a 6 well plate, we would normally need to then be able to tilt the plate, and in the top right you can now see an image of our unidirectional tilting position that would go on the robot that will automatically tilt the plate along onto that short axis so that the liquid goes to the edge of the wells, allowing us to aspirate it without going near those cells. Going up a level from that, a single well plate, or even we would do this potentially with some of the 6 well plates as well, we can tilt in 2 dimensions to move liquid to the corner. So this particular device is slightly different. It allows us to actually rock the plate in all dimensions and stop it at a given position. So we might tilt a 1 well plate on one axis to the short axis and go in with 8 pipetters to rapidly remove the majority of the media on there. And then at a second pass, we might move it to the corner to aspirate the remaining liquid with a single pipette tip and before we put our new media back on top. Pipetting control is absolutely critical to careful cell handling. As I said earlier on, this is a software issue, and how we take control of that pipetter really defines how we're able to recreate some of those potential issues we might face in transitioning from a manual process to an automated one. So I'm going to show you a video in just a moment based on these stills that I can't speak whilst the video is playing, so I'm just going to talk you through it now to say that this is one example of how we will recreate those complex manual movements. And you'll see 2 videos playing in parallel. The one on the left is actually a manual pipetting action, just showing how you would wash media over the top of some cells in a 6 well plate, and you'll see the motions are clearly something we can't do in an automated fashion. On the right, you'll see us recreating it in a very similar but different way, where we can tilt the plate in that same way, and then we can move the pipette to the right and left as we do those pipetting motions. So if you would play the video now, please. So hopefully that's given you a good example of how we can mimic something that maybe is thought to be a difficult thing to transition to automation. I have a second example here as well that I also want to show you, which is also a very simple motion of shaking. And you can see a similar set of videos here on the left. We have a shaking action delivered by someone holding a plate onto a bench. And it's just an example of how we would mimic that in an automated point of view by shaking in a similarly linear fashion. So if you could play the second video, please. And so hopefully that showed you another example of how we could mimic the kinds of things that you would do manually in the lab on an automated platform to work with your cells. When we come to things like shaking, we can actually control the speed of the shaking in a linear fashion. We can also move to doing an orbital shake and control the things like the amplitude by using different shakers, and also the speed that we would want to shake at. So these are both good examples of some of the tools that we have at our disposal to recreate some of those manual motions. The next area I wanted to speak about from our toolbox of things that we have to be able to handle cells is how do we deliver media. This is often overlooked when we're designing systems or when people are designing automated systems, because the amount of media for even a relatively low throughput experiment can be quite vast. So just to touch on a few of these points, typically media is stored on the deck of the robot, and that could, for a low throughput activity, just be some kind of disposable reservoir. That's very common on a Biomek 4000 type solution. When we're looking at something higher throughput that we might be running on one of the Biomek I series, we typically would want to deliver media in some kind of refilling reservoir. And the image on the top right is actually something specifically designed for the cell culture market, which is an automatic refilling reservoir that has 4 segments in it. So it only occupies the same position as one plate on the robot, so you don't lose a huge amount of deck capacity to this kind of system. But it allows us to deliver 4 different media types to the deck and keep those media temperature controlled on deck as well. To go with that, we can also do inline media heating. Clearly, if we're constantly refilling a reservoir on deck, then we might be delivering, if the media is stored chilled below deck, a chilled media into a warm environment, and we don't get a very good consistency in temperature. So we can actually warm that media as it travels towards that refilling reservoir, just to allow us to ensure that we're not shocking our cells with something that's a different temperature from what they're expecting. Another way, and certainly this isn't all of the ways that we might deliver media, but another very common way is to integrate a dispenser, and typically we use devices like the Thermo Multi-Drop Combi or the Biotech Multiflow, which we would integrate directly on the deck of the robot. And these are suitable for delivering one media type most commonly in a very large volume. And one of the advantages of this compared to the refilling reservoir would be that the system is typically sealed. So you seal a bottle onto the dispenser, and then that doesn't get exposed in the environment until it travels out of the nozzles into the plate. So again, it's just some examples of how we deal with some of these media issues, of how do we get media that maybe needs to be kept warm or chilled below the bench of the robot to the system in the volumes that we require in order to process the number of plates that typically pass through these kinds of systems. So, whilst not exclusive, those are some of the things we have in our toolbox that help us to solve some of these challenges around handling cells. One of the other main challenges I said earlier on is really about software. How do you control these systems? And so I just want to spend a bit of time talking about that now. This is a block diagram just showing at a very high level our software hierarchy, and going from bottom to top, the purple box represents our liquid handling software, Biomek software, which will control all of our pipetting parameters. We then above it in the red box have SAMI EX, which is our planning scheduler, which allows us to do that daily task that I talked about earlier on. So if we wanted to process 40 plates per media exchange, that is typically a SAMI task. And then the bit that I want to focus on is the piece above that in the orange box, which is something quite unique, which is SAMI process management, which allows us to link together those daily tasks into a process that operates over weeks or months and control all the data and decisions that go with that. And the data and decision-making facilitation is really handled by this blue box on the left, which is our DART software, which Tim's going to touch on in a bit more detail later on. Just to show you this in a slightly different way, and this is a fairly busy slide, but if you'll just walk through this with me, at the very bottom we have a representation of our liquid handling software, the Biomek software, and the kind of tasks that would facilitate are at that liquid handling level, so removing supernatant and adding media as an example of the two steps in the media exchange. SAMI would then bring those components together into that one media exchange method and allow you to run that for multiple iterations. SAMI process management, going the one level above that, would allow you to tie that media exchange method in together with maybe your passaging method and other methods as part of your entire process. And in the background, DART is then handling all the data that goes with that and allowing you to report on that. So as we said before, cell culture processes present a challenge because they're long and complex. So speaking a bit more detail about process management, what that's doing, I'm going to ask some questions here. So how do I connect multiple automation methods that are days apart? For example, these are all independent SAMI type methods. These are all independent daily tasks. Seeding cells, exchanging media, and checking complemency, each spread apart by a 2-day incubation before we maybe then make a decision about going into some kind of scale-up. How do I make well or sample-based decisions within this process? Complements very often drives the day that we actually passage those cells. How do I keep track of multiple batches? It's very common that if we have a 3-month-long process, you don't want that to be the only thing your system is doing. There's a lot of spare time in there. And so how do I build in maybe a second or third iteration of those, or second or third batches into that process? Then that raises some other questions. Do I have capacity to even do that in the system? And what is the implication for my existing run that I have in there? And of course, then you have some own questions when you get to that level of interleaving. Where are all my samples and plates at any moment in time? And where is all my plate data? And these are all the kinds of questions that process management is designed to solve. So SAMI process management connects plates through multiple SAMI methods, those daily tasks connected into a process. And it also then allows you to run multiple iterations of that processes simultaneously and concurrently. SAMI uses this DART technology, the data handling technology, to bring data from previous runs to the current run, so we have continuity of data, and allows you to know where all of your plates are at any moment in time in order to keep your system organized. The main user interface that I'll show you very briefly now is the calendar module, which really shows you your system resource usage and helps you to plan your tasks as well. This is just a snapshot view of how you would design your process. And if I can just draw on here, these elements are our SAMI methods, our daily tasks. These parts at the very beginning is labware entering the system, and then you can see they're separated by those 2-day incubations. So we can see here very simply how we're building out a process linking together those SAMI tasks. Having built out a process, you would then want to add that into the system, and what would happen is the user would come in, and this is the most common user activity, is to come in and say start a new process. You choose your date and your time, you add in your first step, and then SAMI process management adds into the calendar every subsequent step. You would then need to go through a process of resolving conflicts. So it will tell you whether you are planning to do something at the weekend or evening. Maybe you're happy to do that. We have many of our users that are. Most people don't want to come in at the weekend and would rather avoid that. And so they want to figure out how they would approach that problem. It will also help you understand whether you're going to reach an overcapacity of the system. We only have a certain capacity inside the incubators typically, and adding more and more batches into the system may not be possible. It also helps you identify overlapping tasks as well, and that may cause you to want to move a task out to a consecutive day. If you do need to do that, then SAMI process management then will also move all the subsequent tasks, so you can try and maintain your process as close to the original intended use. And here we can see a final snapshot of the calendar module, just showing us several iterations of a fairly basic 8-day process overlaid on top of each other. And you can actually just see in the bottom part of that window, if I was to try and run this particular process, I do have a number of tasks that I would need to resolve in terms of overlapping activities because of the way that I've built this out. One final part and function of SAMI process management I want to touch on is the in-process decision making. This is one other further problem. So in a typical cell expansion method from 96 well plates to 24 well plates, we only really want to move those on to the next step when they reach a certain confluency. We would typically use an in-process imaging system to do that, which I'll come to in a moment when we look at the CLD system. But our cells all grow at different rates, so how do we deal with that? And so here you can just see on the flow chart on the right, typically what happens is the cells come from the incubator, we measure the confluence, and then some wells move into the passaging route, and some cells do not. They get passed back into the incubator. This means we now split our plates into different groups at this stage, and depending on their process stage, and SAMI process management can handle all of this for you. It will also help us to decide at what point we want to ditch those plates as well. So we may decide that some wells are never going to reach the confluency to move on, so it also helps us to eliminate cells that perhaps we don't want to passage at this stage. Clearly, a single iteration of SAMI won't be able to handle this, and so SAMI process management is the tool that we allow to both make that decision and handle all of those splitting well groups up and keep them in process. So moving on to the final part of my slides, I want to talk about an example automated cell line development system. So this is actually a live system we have out in the field that is trying to develop cell lines that exhibit distinct antibody production functionalities in a fully automated fashion. So this is processing a very large number of cells beyond what we can handle manually in order to screen for antibody production functionalities and scale the ones up that we want to carry forwards. The process that the customer has here, broadly speaking, is that they are going through a seeding process into an expansion. We are also screening during that expansion for antibody production and growth criteria. And then that can then split out downstream into cryoconservation or filled belch cultivation before going into other analytics. And actually the bit of the process that we're interested in is purely this expansion part here. That expansion part operates primarily about one of these per well decisions that I've already mentioned based on using a clone select imager to measure confluence, and we use that confluence to drive which cells pass through in the process. So the system looks like this, and I'm going to go into a bit more detail of this over the next couple of slides, but it's based around a Biomek i7 dual-arm liquid handler, and you can see there are a number of devices that are integrated around this. As we look from the rear, you can see we have a robotic arm that is integrating us to a few further devices that maybe weren't so visible from the front view. To speak about this in a bit more detail, looking at it from the front, we have that Biomek i7 dual-arm liquid handler, which is doing the vast majority of the liquid handling on this particular system. Behind that, we have that robotic arm, which is integrating those devices behind. To the right, we have an automated CO2 incubator. So this is controlled CO2 levels, this is controlled humidity, much like any of your cell incubators that you would have in your laboratory. That CO2 incubator is linked by a plate shuttle directly to the deck of the robot, so we don't have to pass through the robotic arm. And then we also have a dispensing device integrated on deck, which on this system actually serves two functions. It both seeds cells into 384 well plates at the beginning of the process, and it delivers media to those plates as we move on into 96 well plates also. I want to touch on a bit more detail on the analytical devices that we have on this system. So the first one that we use, which was integrated on the right-hand side, is a ViCell. This is a Beckman Coulter device that counts both cell numbers and viability, and presents us with a couple of data challenges around the fact that we gather a single data point per run, which needs to be mapped back onto a plate. So the ViCell can only process one sample, which is typically coming from a 96, 24, or 6 well plate. And of course, those cell counting data does drive pipetting steps, and we've recently released some excellent publications on how we can do that very reproducibly. The next analytical device, which is at the rear and is integrated via the SCARA robot, is the Octet, which is from Pool Forte Bio, and that does label-free analysis for determination of affinity, kinetics, and concentration. In the context of this particular workflow, we really just use it for calculating or gathering antibody concentration data, which we then use to drive hit-picking information for picking high producers. The final device that I want to touch on is the Molecular Devices Clone Select Imager, also integrated to the rear of the system. And we're using this, it can do some other detections, but we're really using this to gather our confluence data, which then drives at a well-based level where we passage or split those cells. And all of those data from those devices also needs to be accumulated and tracked through the system so that we can understand the growth profiles and expression profiles of those different cell lines or different samples that are passing through the system to final scale up. So just in summary of my part of the talk here, we do have a wide variety of cellular solutions out there that utilize a lot of the same tools, but we've installed base systems for both cell line development, as I've just shown you, cell line maintenance for high numbers of cells that need to be potentially turned into assay-ready plates, monoclonal antibody production, iPSC stimulation screening and cell culture, as well as 3D cell culture. We have some dedicated tools that help us to solve those particular challenges around cell manipulation. And probably more importantly, we have some software tools that allow us to manage these processes with in-process decision-making as part of that package, and that's SAMI process management. So at this stage, I'd like to hand you over to Tim, who's going to now take you on a bit of a journey through how we solve data problems for those cellular workflows.
Thank you very much, Russell. That was excellent. And just as a reminder, please be thinking about any questions. We'll leave some time at the end to take those. I look forward to seeing what comes up. I've been working with automation and with robotics and scheduling for over 20 years, and I can tell you that 20 years ago, the challenge was really about moving samples through a system, and sample handling was a big challenge. But today we would consider that mostly a solved problem. And so today's challenge, where the more the cutting edge is to make sure that you're managing your data along with your samples, and that's really the impetus behind our talk about having two different layers of integration, both the sample management and now I'll go into the data management. To repeat Russell's slide here, looking at the continuum of liquid handling and automation products that we have, I want to start pointing out where some of the data challenges come in. And the data challenges come really at every level. Handling data is not something that occurs only at the most complex cell processing systems, but even in individual hit picking, in seeding or feeding operations that are done even at the entry-level automation systems, we still have those data management challenges. Again, reiterating the list of challenges that Russell prepared for you, there are a number of data challenges that are intermixed with the sample processing challenges. The fact that we have long processes that run from weeks to months, maintaining an understanding of the traceability and the information being processed is important. Having a large number of plates in the system adds layers of data which just accumulate samples, wells, media types, concentrations. You want data-driven decision making. And then handling liquids and driving pipetting, hit picking, those are all elements that come into the data domain. So that we're clear, there's a lot of different ways to look at data. What are some things that I see? So certainly as you bring information in from from an Excel spreadsheet or from a LIMS system, but there are types of data. This is more of informal data, which is important, but can still become useful as you're looking back at your results later. Now, what was my lot number? Did I write that down? Did I take good care of my record keeping? Information that's on a plate, or even the Sharpie that you use to indicate how you're processing this plate. These are all things that, if tracked electronically, add to your data record. And the more information you're able to accumulate, the more you're able to use in your reports to draw conclusions, or heaven forbid you need to do some root cause analysis of failure, it can help with that extent as well. So as we look at data through this talk, I want to talk about some specific process level data. It could be something like the identity of the well, and the sample ID that's inside of it. Could be the concentration or volume of a well. Is this well being used as a standard, a control, a blank, or is it an assay well? If we're doing hit picking, is this one that will continue or a well that's left behind? We can log things like the user, the method name, did the method finish correctly, and then as we learn things about the system, we have different analytical devices that will be telling us answers. So these things on the post-its are more of my concept of what data we would be managing as we move through a system. Who is interested in data? Well, in the end, really everyone is. Whether you're operating the system, whether you're managing a lab, if you're investigating and trying to learn something, if you're leading a project to make some sort of discovery, if you're purchasing automation or reviewing to see whether results are correct, all these different people are interested in data. And we need to find a way that we can use the same information to make sure that daily operation happens properly, that purchasing knows the consumables to be buying, that the lab manager is getting the results, and that the researcher can publish, and that as an auditor or maybe a quality check, that anyone who's looking over your shoulder is also satisfied. This is really a multifaceted element, and so we want to make sure we capture this data so that we can serve all of these different constituents. So as we go through these next slides, I'm going to talk about 4 challenges. And as we make a data management plan, I want to really think about kind of 3 different elements that come into play. The way that data is handled is it first is imported or introduced into the system, and then it either drives behavior of the system or is discovered as part of the system, such as in a reader value, and then that information is looked at and some sort of action is taken, some sort of analysis takes place. So those are the 3 steps. But I'll break it down into 4 different challenges, and that's really what we're here to discuss. These 4 challenges, first of all, we'll begin with sample identification. This may be coming from something that's entered. It could be from barcode reads. It could be from a LIMS, from a laboratory information management system. We need to then track these sample IDs through the entire process. Samples into assay plates, tracking samples across multiple systems and after incubations, track them through long-running processes. These are things that Russell referred to in his part of the talk today. After we've been processing the system, eventually we have some sort of endpoint. We have some analysis that's done. So how do we get this information? How do we bring it in? Because data exists in many different formats on disk. These data formats are changing constantly as new readers are introduced to into our industry, and anything that we learn will then drive the next step, such as hit picking or clone selection. And then finally, once we've gathered this information, we need to report on it and then publish that back into whatever business process is used for the next step. Perhaps that would even be part of a research paper or a poster presentation. So let's break these four challenges down, and we'll begin with sample identification. So where does sample ID come from? It may be imported from a file. It could be something that we retrieve from a web service or from a LIMS system. Today, I'll show you how to generate new identities. So in cloning, you may have clones that come from the same source. So how do we uniquely identify the different clones that we're then selecting for further processing? One challenge with CSV files, the most common way to process data between systems today, is that the formatting needs to match between the output system and the input to the next step. And I just want to identify that copy and paste is not an automated solution. If you're copying, then you are the robot. So let's look at a system and design a data management approach that makes sure that these handoffs are done as seamlessly as possible. So let's take a look at an individual method. This is on a cell culture I-series instrument that's in our Indianapolis lab. And I just want to note two different plates here. We'll begin with clones in a matrix rack, and then we'll transfer those into an assay plate which sits next to it. So if we look at this method on the left-hand side, we have an instrument setup step, and before we do anything data related, we can look at what data exists on this plate. And by default, the Biomek and SAMI software will automatically track the liquid type and the starting volume that is in the plate. So before you even begin, you have data on your plate in the system, whether you know it or not. The next thing we'll do is we'll take the barcode of that plate and the well number, and we're going to create a new data set, and this data layer will be sample ID. This will be the ancestry of every pipetting operation that will follow. So in this case, we'll have the barcode and the well number that moves on. So if we now look, we have created a new data set. It's called clone source, and it has the barcode and the well number that all of this began. There are other ways of bringing information in. DART also has an import tool which has a way of dealing with, flexibly dealing with comma-separated value input files or importing from a database. And this is another way to bring information into the system. So this is how we'll look at sample identification. The next step is that once you have sample IDs established in the system, if you're bringing this onto a liquid handler, you're going to be doing pipetting. And so in that case, we need to have sample traceability. And this traceability, it will be watching how we move through the system. And why is this important? This is important for three layers. One is it helps you organize your work. It's helpful to your team for internal processes, and it's helpful to others as you look for submission. So why would you do tracing? The question really is, why wouldn't you want to trace your pipetting to know where each well and destination plates came from? And while many people will do traceability as needed, isn't there value in always doing this? What if you could get traceability for free? Well, that's something that we can look at with the Biomek software. You can have many different data sets associated with each well in both the Biomek and SAMI software. And then in this well, we can have different types of data which can all coexist. And then all of it gets tracked when transfers are performed, whether in Biomek or in SAMI software. So in this case, we have a very simple animation where the pipette tip will aspirate from a source well, move, and then dispense into a destination well. An advantage of working with the Beckman software is that as you aspirate sample, you also aspirate data and then can deposit it into the destination well. So without doing any sort of specific data management tasks, the pipette tip is your data movement tool. And so different data sets will move along to the destination. Let's pick up this assay. What we've done is we're now looking at the assay plate, and we've transferred one column of information from the matrix rack into column 1 of the destination plate. You can see the sample IDs have been picked up. When we perform a serial dilution, we're diluting across the first 6 columns, the left half of the plate, if you will, and those sample IDs are copied through all of that as well. So later, when you're looking at your curve, you can see the origin of each of those samples that's in the plate. And you get all of this for free as the sample and data are pipetted together. So now let's turn the corner just a little bit to start to look at how we bring information into the system. In the end, you're going to target some sort of plate reader in order to bring information in. Our software all hinges through our Silas technology in the blue square. And so As we look at the different layers, this is again repeated from Russell's talk, where we have different pieces of software that come into play depending on the complexity of the system and the length of the workflow. But we will use these different pieces together in order to get our results. So why are we running these assays? Because we need to get some sort of outcome. And this outcome is important for making decisions, such as in hit picking. And one example of that would be promoting clones for further processing. And we also need this information in reports for downstream processing. As we add new devices to a system, the modality that we use today is not the same reader that we were using 5 years ago. The technology when it comes to cell culture data gathering changes year to year. And so we need to have some way of adding new devices to the system. Likewise, there's no one endpoint reader which gives us all the results that we need. And we'll look here in a minute as to how we can do hit picking on multiple different inputs as we combine the information from 3 different readers. We want to be able to use this information for in-process decision making. If we need to stop the process so that a user, that a human is doing an analysis of this, of course there are times when that's the only way that this can happen, but one goal in a data management plan would be to automate the sample evaluation so that we can connect 2 different processes and bridge those with automation. So if we again look at the Silas bubble here, we see that it's connected to a robot, to a reader, to a washer, and this is a way that we can swap out different devices within Beckman automation. Here are 3 different data producing devices. In the top right hand side we have the Beckman Coulter Vicell, followed below it with the Paul octet. The silver device is the molecular devices Clone Select, and the lower left is the molecular devices i3, SpectraMax i3 with the Minimax cytometer. The Vicell produces cell viability and cell count. The octet produces an antibody concentration. The Clone Select produces confluence. And then rather than using multiple devices, the i3 can do multiple tests, but may take longer in order to make that happen. So if we were to take these different devices, and whether they're all integrated or we're using the data produced as you carry a plate by hand, we would like to do a hit pick which uses the following scenario. Let's pick a monoclonal seed where the cells are growing well and are producing the target protein. This is really the trifecta that we're looking at for cell characterization and for cloning. So we can create a new data set which uses those 3 items as inputs and then creates a true or false to know whether we'll do further processing. What tools would we use to do that? Well, in the Biomek software we can use a calculate data set. We can use one data set in the transfer step or a script node. And then in SAMI we can use a script module. A third way we can do this is using our Dart data management software. We can create a report that has the well identifier, the 3 columns which each have one of the values from above, and then use a formula in Excel to look at a comparison that turns into a true or false value depending on whether that condition is met. And that information can then be pushed back into the Dart database. The final challenge in dealing with cell culture data is sample reporting and getting your results into your business processing system. So we need something that will log all of our activities, follow traceability through the system, and then review these results and push them into whatever business analysis process that we are using. Dart reporting can do this through three different layers. 2 of them are in Excel. One would be an Excel plate map or a tabular report. We can also create Microsoft SQL Server views, and that would be a direct LIMS access, and we wouldn't need any copy-paste through that. We can also use the web for direct drill down, and we can take a look at that. Here's the data acquisition reporting tool. It has 3 pieces to it. It stores all of the data, works with Biomek and SAMI, and gives that view remotely. The key thing that DART does is that it will automatically collect this information and store it in Biomek or SAMI, and it's able to retrieve this information, such as after an incubation, when that plate is returned to the Biomek, we'll be able to react to it based upon the information such as the traceability as well as the data that's been added through a reader. And then in the end, DART is the tool that gives us the best capability to produce reports. One example of what this report might look like is to show the method name, the start-finish time, the plate barcode, the name, and the incubation times, and then information about the sample identity, some processing information shown in green, and then some analytical information. In this case, we have 2 different values taken at 3 different times, resulting in 6 different reader values. But because we have all of this information in the same report, we can correlate our identity information with the analytical information, and those are conveniently located side by side. Using the DART Query Builder, we're able to keep a live link from our report back to the system, and refreshing this information allows us to get new information from new runs. And without generating a new report, we can simply update that report with additional information. Or we can view it in the web using our data browser, where we can view run, labware, and well data and perform that drill down. So to wrap up, we see that a data management plan needs to focus on the 3 components, the 3 activities that happen in data processing. Data import, having data drive decisions within your automation, collecting your data and reporting on it. And if we follow our data management plan, we'll see that certain characteristics come out. An assay with a good data management plan will identify compounds and samples with identity. Data will drive experiment behavior. Data will flow through the system automatically without needing additional steps to process. It will gather information that's learned, such as from a plate reader, during the process. It will correlate your identity, your traceability, and your analytical information, and then preserve all of that information so that you can report on it and drill down, process that into the next system. So hopefully today you've learned something about designing a system and some of the components that go into the hard side and into the capabilities required for pipetting and managing cells, but also how to make a data management plan so that in the end your system can process 2 layers of samples. You have integration both in the hardware and in data management. We'll now pause and take questions.
Excellent presentations, Russell and Tim. Thanks for bringing that information to us. So before we get started with all of your questions, here's a quick reminder about how to reach us today. Questions can be sent via the green Q&A button at the lower left of the presentation window. We'll get to as many as we can, and our first question is your scheduling software compatible with other liquid handling systems?
Hi, this is Russell. I'll take that one. So if you mean by liquid handling systems a dispenser or some kind of washer or washer dispenser, then yes, as an integrated device, we can do that. But in terms of being integratable with other people's core pipetters, then it's not. So our scheduling software and our SAMI process management software is specific to Beckman Coulter automation platforms.
Does automation increase the chance of cell shearing or aggregation, or how do you minimize the risk of cell shearing or aggregation?
So coming back to what I was talking about earlier on with pipetting control, this really is a case of we can mimic what you would do manually with the fine control that we have on the Biomek to achieve the same levels of shearing or aggregation that you might see from that point of view. So no, in a simple answer, automation doesn't increase the likelihood of that because of the fine control that we have, as well as we can utilize certain things like wide bore tips to minimize the impact of cells passing up through the aperture, as well as that fine pipetting control.
I currently culture T75 flasks. Can I use this on one of your systems? And if not, then what are the alternatives?
Yeah, that's a good question. It's often one of the things that we have to think about most carefully when we move over to automation is that the labware that you use manually is probably not the same as the labware you would use in an automated platform. So a T75 Flask is not what we'd call a standard footprint labware for an automated system. So the kind of labware we would use would be multi-well plates, the largest of which would be actually what we call a single well plate, or an omni tray is a particular brand name for one, or there are also automated flasks as well that have a surface area that is smaller than those ones you would use manually, and so you tend to use multiples of them. But at the lower end of the spectrum, you'll be looking at 6 well, 24 well, or 48 well, 96 or 384 well plates most commonly.
Can you describe how automating my data would reduce the copy and paste work in the lab?
Yeah, sure. This is Tim. I'll take that. One of the more common pain points as I talk to users, they tend to have two things. One is mistakes or gaps in data, and the other is having to manually process this information instead. The way we try to design systems is to look at automated ways of retrieving information, let's say from a web service or a LIMS system. We can pull that information in, attach it to a plate, and then with the traceable pipetting that we have, you will end up with those sample IDs right next, in parallel data arrays next to the analytical data. And in the end, what that really means is that you can have your sample ID next to your data very simply, even on long-running processes. And then on the reporting side, we can push information into a LIMS system or allow the LIMS system to pull information from our system, either way. And again, not only does it automate that task and remove the manual step, but it reduces the likelihood of a mistake, some sort of transposition, picking the wrong file. Really, we increase the reliability of the data workflows. It is a little bit more work to set up in the beginning, but then you pay off every time that you run the system.
Can you integrate other plate readers like an imaging reader into a workflow?
Yeah, certainly. We've integrated a number of different imaging readers. One note, I didn't include imaging readers in my slides. The images themselves would not be something that we would attach to our plates as data directly. Perhaps we would refer to those images by file name or by reference. But the scores that can be generated from those reads can be attached as data that can then be used for driving decision making and used in the analytical results.
Can automation be used to optimize culture growth conditions of bacterial expression systems, i.e. E. coli, for time-sensitive parameters such as OD?
Yeah, of course. I mean, bacterial cultures present a slightly different set of challenges for us, and they grow much faster. But as compared to mammalian systems, but automation can still help to process the samples faster and more consistently. As we just alluded to, we can integrate other analytical devices, and typically you would use some kind of plate reader monitoring optical density through absorbance to characterize the growth of a bacterial cell culture. And we have customers out there using Biomek systems to do this kind of thing already, such as selection of successfully modified genes in CRISPR-Cas9 protocols.
Okay, we have time for one last question. So if we didn't get to yours, we will follow up with you via email. Is there a way you could help me to work with my LIMS IT folks? Seems like they're always busy.
Yeah. Everybody's always busy, and the thing that's the reality of today's laboratory is that information is really a key part of it. So hopefully everyone does have a good relationship with their IT folks. One thing we've heard about our DART data manager is that this is a repository of information that can be under your own control. You can have information on your system and processing your samples, and you can ask your own questions to get some quick results. Now, this isn't intended to replace any business important decision-making tools. The import and export to a LIMS system, for instance, should still happen. But if you just want to check on your controls or build some simple reports, maybe something you can send to your boss that gives some summary information, that's all very easily done. And so I find that we still work with IT and bioinformaticians when we're importing and exporting data, but then using like the Dart web view to look at controls, to look at, am I getting results out of my reader? Do those results look decent? Are they at least registering? These are the types of things you can do and inspect while the system is running. And you can have access to that very easily. People find the web browser. You don't have to go back into the lab. You can do it from your desk, and that access has been very convenient.
I would like to once again thank Russell Green and Tim Sherrill for their presentations. Do you have any final comments?
No, from my side, it was a pleasure to speak today. I hope that was all very informative for you. And if you have any further questions, then of course you can make contact with us through the usual channels.
Okay. And did you have any final thoughts?
I just appreciate I'm pretty passionate about making sure that we look at managing the two flows of through the lab, both the data as well as the samples. And I think if everyone makes some sort of thought with regards to a data management plan, that will pay off in the long run, and you will thank yourself in the future.
Well, I would also like to thank our sponsor, Beckman Coulter Life Sciences, for making it possible to bring this presentation to you. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Today's webcast will be available for on-demand viewing through May 2018. You'll receive an email from us alerting you when it's available on demand and posted on labroots.com. You're welcome to forward this announcement to any colleagues who weren't able to join in today. Thanks for logging on and participating in today's broadcast. We will see you next time.